Good morning to one and all. In today's lecture, we'll discuss about the noise in analog modulation. So, first we need to know what is noise. Noise is any unknown signal which distorts the transmitted signal, which affects in the recovery of the desired signal. So during transmission, there is introduction of noise, which is additive in nature and hence called as additive distortion. Now, in communication system, the transmitter and receiver are basically made of electronic devices and are the major source of additive in nature. So, there might be electromagnetic signal that interfere during the transmission and the signal becomes noisy. So generally a receiver signal is a function of time that is denoted by RT is equals to ST plus WT. So we can see that the received signal is a combination of your transmitted signal along with your white Gaussian noise, that is also known as your front end receiver noise. So your received signal is denoted by RT. Now, in order to find the quality of performance in analog communication system, the first step is to determine the signal to noise ratio, that is the signal power upon noise power. So to understand the noise performance, we consider a receiver model. Now here we can see we have an input signal that is empty. It is passed through a transmitter via a channel medium. It will be received at the receiver end. Here we have a channel noise that is denoted by WT. Here we can see that we have an SNR input at the input side and SNR at the output side. So we can see that the SNR is improved as the signal power or transmitted power get improved. So the maximum value of your transmitted signal is limited by some factors, that is the cost, channel capacity and the interference. Now we will be understanding the noise performance. For that we consider a receiver model. Now here we can see we have a modulated signal that is denoted by ST and it is combined with a white noise that is denoted by WT. Now it is passed through a band pass filter. So the function of the band pass filter is to convert the front end receiver noise, that is your WT, into your filtered noise that is denoted by NT and having the band limited. So here we can see your WT is get converting into your filtered noise, that is NT. So here with respect to that we have this SNR input as well as your SNR output at the receiver side. Now here we note a point that the power spectral density of your front end receiver or your white noise, that is denoted by SNF, is equals to N0 by 2, where N0 is the average noise power per unit bandwidth. Now to compute noise power, noise is measured over a specified bandwidth. So here we can see that we have a front end receiver noise that is passed through your band pass filter and it get filtered noise. So at the output we get the filtered noise per output. So we can see the ideal characteristic of band pass filter noise. Here we can see that this is your band limited, your carrier frequency FC. With respect to your power, we have drawn the ideal characteristics with respect to your power spectral density and frequency. Here we have a carrier frequency that is band limited, denoted by BT, and the power spectral density is N0 by 2. Now here your N0 is the average noise power upon per unit bandwidth. So we can see that one bandwidth, that is the average noise power, is equals to N0. The value is N0, while the transmission bandwidth, its value is given as N0 B suffix T. So we can see that at the filtered noise power at the output we get N is equals to N0 B suffix T. Now while practically generally carrier frequency is for greater than transmission bandwidth. So the filter noise is also called as your narrow point noise. So the narrowband noise, that is denoted by NT, that is equals to NT is equals to NIT cos 2 pi FCT minus NQT sin 2 pi FCT, where NIT is in phase component while your NQT is your quadrature component. So at the filtered signal, at the demodulation, after demodulating, we get this filtered signal, that is XT is equals to ST plus NT. So by this we can define SNR using an expectation operator. So here we have defined the signal to noise ratio is defined by SNR is equals to expectation of S square T into expectation of N square T. Here E is used as your expectation operator. So the squared signal level is proportional to your power. Now the ratio of your average signal power to the average noise power, which is measured at the receiver side at particular point, having its own particular importance as well as its value. Now after discussing a receiver model, your SNR at the input side and output side, we are ready to compare between your different analog communication. So here we can see that we have an input signal ST combined with your white noise, that is your front end receiver noise, and here we are receiving at the receiver side your SNR output, and here we have SNR input. So at SNR input, that is at the front end of receiver, called as your pre-detection SNR. So basically your SNR input is always known as your pre-detection SNR, that is used for the quality of transmission link and front end receiver. At SNR output, at the output of the receiver, it is called as your post-detection SNR, that is used to measure the quality of recovered information bearing signals, for example, audio, video, etc. Now, after discussing the receiver model at the SNR input and output side, we are ready to compare between different analog communication. So here we will be seeing the reference transmission model for analog communication. This is a basic model. Consists of a low pass filter having bandwidth equal to the message bandwidth, so that it can pass the message signal and reject your out of band noise. Here at the input side, the message power is added by your channel noise, and at the output of your low pass filter, we get a filtered signal that corresponding to the information bearing signals. So we can see that it is measured at the receiver input. Your SNR reference will be equals to your average power of modulated message signal upon the average power of noise measured in message bandwidth. So this is also called as your SNRC, that is your channel SNR. From here we can see the figure of merit, that is equals to your SNR output upon your SNR reference. That for the better performance at the receiver side, it must be the higher value of FDM, depending upon the type of modulation schemes that we have used. So here the first one is your SNR input, that is measured before the signal is demodulated. Second, your SNR output, that is measured after the signal is demodulated. And SNR reference, that is based on a baseband transmission scheme. So we can say that the figure of merit is equals to your SNR output upon SNR reference. From here we can see that it is a dimensionless quantity. So this was all about the noise performance. In next lecture we'll discuss about the noise in double sideband receiver. Thank you.